So last time we discussed, last time in this playlist or in the series of lectures that we've been making, we last discussed the Dirac equation. So, um, so the Dirac equation, recall, is I is actually up here. So it's over here. So I times the derivative, general derivative, times the, so this is a shorthand notation basically. So this is I times, not really mu, gamma. Is it gamma? No, mu. And then this is times the times the, not the Pauli matrices, but rather the Dirac matrices. So this is my Dirac matrices constructed with my derivative, my differential operator, and this is minus m acting on the wave function is equal to 0. So, right, we discussed this. We tried to derive it last lecture and sort of talk about a little bit. So I teased you guys on the implications of that kind of stuff, and we tried to solve some problems. So we essentially took a trip through history and talked about why exactly the Schrödinger equation is not a particularly good quantum theory, especially when we start talking about phenomena that occurs at the speed of light. So yeah, that's what we did last time. So today we're going to be picking up from where we left off, and we're gonna solve the Dirac equation, and we're gonna see how that relates exactly to Femboys and Tomboys. So today we're gonna be discussing mainly about something called the Dirac Sea, and yeah. So in the last lecture we left off with the last object we discussed about in the last object we discussed last time was something called a Dirac spinor. So the solution, so a solution to, so any solution, right? So any mathematical object or whatever, what have you, that solves the Dirac equation is something called a Dirac spinor. So it's some psi, which I can express as a four component vector or something. It's not really a vector anymore because it acts differently from a vector. In fact, it's called a spinor. It's composed of four complex numbers, and yeah, we really left off there. And now, in this lecture, we want to ask, what exactly is this thing? So what is a Dirac spinor? So it's essentially what we want to answer in this lecture, and we also want to know, what does it imply? So what does the existence of a Dirac spinor imply, and what happens if we solve the Dirac equation? Okay, so hopefully we'll be able to answer those three questions in tonight's lecture. So to begin, let's go back to the original way we expressed our Dirac equation. So that's I h bar times the time derivative of acting on the wave function is equal to negative I h bar times c times my alpha matrices times the Laplacian acting on the wave function. So this, yeah, my alpha matrices, and then plus my beta matrix times mc squared psi. And in today's lecture, we will assume the block form of our alpha and beta matrices. So mainly, I will say that alpha sub I for I in index running from 1 to 3, and 1 being x, 2 being y, 3 being z. So that's equal to the following matrix. So that's 0, sigma I, 0. Wherein sigma I are our Pauli matrices, Pauli spin matrices. And my beta matrix. I actually made a I made an error in the last lecture. It's not the um, so the identity matrices that it's supposed to be composed of are supposed to be along the diagonal rather than the other diagonal, you know. So there. So we'll assume this, and I'm assuming you guys already understand this or watched the last lecture. So again, because I'm just reiterating what I said in the last lecture, because alpha and beta are 4 by 4 matrices, the Dirac equation is in fact a system, right? It's a system of 4 equations which are our supposed wave function psi must satisfy. But now, because of course it's a 4-dimensional structure, or it has 4-dimensional structure, things are different now. So it doesn't behave normally like how a vector would behave, or how a normal wave function would behave with the Schrodinger equation. It's now a spinor, a Dirac spinor. So again, to begin solving, we're gonna assume a free particle with the following wave function. So to solve, we begin with the plane wave solution. It's always the plane wave solution, the simplest prototype for a solution for the Dirac equation or any equation that involves the wave function is of course the plane wave solution. So off the form, so let me try to get this right. Psi is equal to some spinor u of E, and then the momentum P times the, so E to the I over H bar times the momentum P times X minus ET. Or of course, P is my 3 momentum. So if I sub this solution into the Dirac equation, I would get that my IH bar dt acting on the wave function is equal to E. So I pull out an E factor because I'm really only differentiating with respect to t. The rest are treated as constants. So I'm pulling out an E term, and this is times my U times E P, and then that's times the exponential function with nothing changed inside. So H bar P is X minus ET. And I'll just shorten this U of EP into simply U. So note that this U over here is a spinor. So it's not just a regular vector composed of E and P, but rather it is now a Dirac spinor. Okay. So this is for the left hand side. So what about the right hand side? If I sub it into my right hand side and clear out the algebra, I get that my negative IH bar C alpha contracted with Laplacian acting on the wave function plus my beta MC squared psi is equal to essentially, so C alpha dot P plus beta MC squared times U, and then the exponential part. So I'm just gonna write dot, but this is the same thing as this one over here, and that's U is the same thing as the one over here, except we pull this term over here from inside the exponential. Okay, so since these two are equal, of course, next I would equate these two. So what you'll notice right off the bat is I can so when I equate these two, I can cancel the exponential. So when I cancel the exponential in equating these two equations or these two expressions, I would get the following expression for UEP. So E U of E P is equal to, so this is the, I'm trying to get this right, C alpha dot P plus beta MC squared times u of EP. Okay, so this is another form of the Dirac equation, and this is in fact called the time-independent Dirac equation in momentum space. So this is the time-independent Dirac equation in momentum space. All right. So what you guys would notice is that if we consider a stationary particle, so let's consider next a stationary particle. So this is our case 1, stationary particle. So it's a stationary free particle. So no force is acting on it, and it is completely stationary. So that means my free momentum is essentially the zero vector. And what do I mean by that? It's essentially just 0, 0, 0. Okay. So if we consider this type of particle, we get that. So this would imply that, okay, if I plug my momentum into this into the time-independent Dirac equation, I would get E u of E 0 vector is equal to beta mc squared, because of course this would cancel to 0. Okay. Beta mc squared u of E 0 vector. Okay. So if I divide by mc squared, I would, so let's divide by mc squared. Of course, that's going to cancel, leaving me with an E over mc squared. U of E 0 vector is equal to beta U of E 0 vector. Okay. And if I let lambda, suppose let lambda equal E over mc squared, we would then get beta U of E 0 vector is equal to lambda U of E 0 vector. And this looks oddly familiar. This looks like an eigenvector eigenvalue equation. So except this time it would be something called an eigenspin or eigenvalue equation. So wherein, of course, my eigenvalue is lambda. So it's my eigenvalue. And beta is, of course, that matrix. So it would look A, so x is equal to lambda x. It would look similar like this, except now x is not a vector but rather a spinor. So it's an eigenspinor eigenvalue equation. Okay, so what then? So if I write U as the following. So recall that last time we can express U as a UA and UB. Okay, so no, we can write it as a UA, UB, and of course my beta is the same block form. So it's I, 0, 0, I. So just keeping in mind that I is the 2 by 2 case, or the 2 by 2 identity matrix. So we have a 4-dimensional structure. We get essentially, this is I, 0, 0, I multiplied to UA, UB as equal to lambda times UA, UB. Okay. So if I do the relevant matrix multiplication on the left-hand side, I would simply get UA and then minus UB is equal to lambda times UA, UB. And this gives me 4 coupled equations, but ultimately it would say So it would mean, or what it would apply is UA is equal to lambda UA, and UB is equal to negative lambda UB. And of course, obviously, um, I can cancel essentially my UA and say my eigenvalue is equal to 1. Um, but really, this only holds when UA is non-zero. Okay? So, if UA is non-zero, then I would get that my lambda, my eigenvalue, is essentially plus minus 1. And um, my UA would be some combination of spinors phi 1, phi 2. I'll use phi. Okay. And if now my UB is non-zero, my lambda could only take on a negative 1 value, and of course my UB can still be expressed as my psi 3, psi 4, phi 4. So again, this next implies moving my mouse. Okay, this implies then that beta u is equal to lambda u. Of course, I'm just reiterating what I said a while ago, but this implies that we have two possible eigenvalues. So of course, lambda takes on a +1 or a -1. So if we choose the +1 branch, so the positive branch, I get E equals mc squared. So in the positive branch of the eigenvalue, I get E is simply mc squared, which is the rest mass energy equivalence that we normally have for normal matter. So in the negative branch is where things get interesting. My E is negative. So it's negative mc squared. Okay? So you may think that this is some mathematical glitch or something, but you guys will find out later that this is actually something that the math insists. So rather than our physics needing the math to conform to it, the math requires the physics to conform with it, and thus our assumptions with the universe or subatomic particles. Okay. Right. Okay, so if I consider, if I consider lambda is equal to +-1 and simplifying the block equation, I would get essentially UA is equal to UA and minus UB is equal to UB. Okay, so far so good. And so this implies that UB must be 0, but then my UA must be some positive definite value. So UA must then be non-zero, and it is expressed as my phi 1, phi 2, where phi 1 and phi 2 are complex numbers. Okay. I hope you guys can still see that. Now, so because of this, a general positive energy solution takes on the form U plus. I'll call it U plus. It's equal to UA, UB is equal to UA 0. So this is the positive branch because UB has to be 0, UA is itself, and then yada yada yada. In the end, we get phi 1, phi 2, 0, 0. Okay, so that's my U. And furthermore, I can express it in terms of two basis spinors. So just like how we can express vectors in terms of basis vectors, I can express my U plus in terms of basis spinors. So my U plus can be expressed as a phi 1 times the unit basis spin or E1. Uh, so plus my phi 2 E2, where my E1 is the basis spinner pointing at 1 0 0 0, and then my E2 is my basis spinner pointing at 0 1 0 0. And you guys can see the pattern from here on out. If I consider next the negative branch, it would then be U minus. Okay, so it would be U minus. So considering, so let's go to the negative branch. Considering phi is equal to -1, and then I do the same procedure, I would get U minus is equal to UA, UB, but this time UA is 0 and B takes on a negative form, essentially. So it would be 0 and then UB. Okay, so far so good. And then recall that I can express my UB as a phi 1, phi 2, right? Phi 3, phi 4. So it would then be a 0, 0, and then phi 3, phi 4. Okay. And just like with my positive branch, I can express my negative branch in terms of basis spinors. So this is my phi 3 E3 plus phi 4 E4, wherein E3 is the basis spinor pointing at the 0, 0, 1, 0 direction, and my E4 is the basis spinor pointing at 0, 0, 0, 1. Okay. So good. So in general, all in all, my system has two states, U plus and U minus, which can be expressed, of course, in terms of basis spinors, E1, E2, E3, and E4. There. Okay. So if I go back to my plane wave solution, okay, so we found the U term in our wave function. So then my wave function would take on two forms, the positive and negative wave function. But you guys will see later that the negative wave function doesn't imply anything bad. Okay, so it's not bad for our physics. You guys will find out later. So this x, so e to the negative m c squared t over h bar. And then psi is equal to u minus e to the minus mc squared t over h bar. And again, I can express this in terms of my basis spinors. So this is phi 1 e1 e to the minus mc squared t over h bar, plus my phi 2 e2 e to the minus mc squared t over h bar. And then this is equal to then the negative branch would give me so this is 3 e3 e to the minus mc squared t over h bar plus phi 4 e4 e to the minus mc squared t over h bar. So now, because we're able to express our wave function in terms of our basis spinors, what we're essentially saying is that we're essentially spanning all the possible solutions. So all solutions, we have considered every possible solution, and it's necessary that the negative branch be considered as a solution. The math insists. Okay, so if I were to say not consider my negative energy because it looks wrong to me, or it looked wrong to physicists back then, I would be throwing out half of the story. Okay, so the math insists that the negative states be considered. So I'm rehashing essentially what other physics YouTubers have been telling you guys already, and I really should be assuming that you guys already understand this, but it's important that you guys understand that it's important you guys appreciate that this type of thing was discovered, or this type of thing is necessary in order for the physics to work. Okay. Okay. So what now? So again, so what's next? We have fully characterized our wave function. What do we do next with it? Of course, we find the probability density. So again, the probability density of our wave function, so rho of xt is essentially equal to the wave function times its Hermitian conjugate times itself. So again, because because our psi is now a Dirac spin, or regular complex conjugation doesn't work with it. If I take the complex conjugate and I multiply with the original wave function, we are multiplying two fundamentally different mathematical structures. So we need an analog, and of course I discussed in the last time, that's given by the Hermitian conjugate. So again, let's rewrite our psi in our rest frame psi wave function in the following form. So psi is the sum of our phi I, E I. You know, it's a bit confusing considering we have an I, so I'm gonna use a different index. In my notes it's an I, but let's use a different index here. So summation over J, let's say J, phi J, E J, E to the I over H bar, E sub J T. Because you know there's a complex number over here, and then sometimes I is used as an index, and you know that stuff already. Wherein of course my E can take on two values. So E12 would be MC squared. So this is for J is 1 and then 2. So for the sum. And then E34 is a minus MC squared. Okay. So what I'm saying with this expression over here is, or this equation is that for the first two terms, my energy is positive, and for my last two terms, my energy is negative, as what our derivations imply. Okay. So if I take the Hermitian conjugate, I will be flipping signs and taking the complex conjugate of the complex components. So my psi dagger would then be the sum over all j of my phi j complex conjugate, E sub j dagger, because E is a spinor, and then E plus I over H bar E sub jt. Okay. So if I then multiply these two together, so my rho, which is equal to the Hermitian conjugate of our wave function times the wave function, is a combination of two sums. So this time I'm gonna use two different indices. So let's use Greek indices for now. It's just a shorthand. So let's say psi and mu. Okay, because again, if I put I over here, it might be confused with the imaginary component that's over here. So I'm gonna use mu and nu. So don't be confused with that one. Okay, so it would look something like, so psi conjugate mu phi conjugate nu, so, and then E mu dagger E nu dagger. Oh no, the nu doesn't have a dagger, my bad. There. And then E to the I over H bar E sub j, no, not E sub j, E mu minus E nu times T. So it's a difference now. Because of course the other one has been sign flipped and then etc. Okay, so that's pretty neat. And we would know that um, my E mu, so my E mu dagger times E nu is non-zero, and my uh, E dagger E nu would equal 1 only if my mu and nu are equal. You guys can check that out for yourself. So, yeah, if and only if that's true. And that would then imply that the sum, so every component is essentially positive in our row. So our row ends up being a sum of moduli of the complex component of these Dirac spinors. And of course, the moduli, so the modulus of a complex number is always positive. So in summation, I would get this the sum over mu of my um, of my complex components, I don't know, squared. So the sum of the moduli would be greater than or equal to 0. So that would then say, or that would then mean that my probability density is greater than or equal to 0. And that means three things. The first one is that rho is always positive definite. So for of whatever choice of our psi is, it has to be such that my rho is positive definite. Okay? And next, my rho is then constant in t because, of course, it at some point over here, our time-dependent term, the e cancels out, or it's essentially it cancels out in the beginning. We saw that with the solution, or trying to find my u. And um, this sum over here involves the negative terms. So the negative components, so my the one with the negative energies, contribute positively to rho. And that's what I'm saying with we only get half the story if we disregard or throw away the negative values or the negative branch, because then we would only be having half of the picture, half of the full picture of our wave function. Okay, and this fact over here, oops, this fact over here, I'm trying to get this box right. Yeah, this fact over here implies, of course, that the inclusion of negative energy branches lead to positive probabilities, only positive probabilities, never negative probabilities, because again, the moduli of a complex number is always positive, and we're summing over all moduli of these complex overall moduli of these complex components. So of course we get something that's a positive number, always a positive number. So if we consider the negative energy branch, we don't get negative probabilities like we would have when we considered the Klein-Gordon equation. Okay, so again, that's another justification on why we cannot just throw away or disregard negative solutions. So why, in the first place, you're probably thinking, okay, why don't we just throw away the negative branch and not consider them, only consider the positive ones, because they've been sort of a pain in the ass so far, right? Like you've been thinking that through the beginning, like why don't you just throw away the negative part? But I just showed you guys that we cannot just throw it away because we'd be missing half of the story. Okay, and you guys will see why exactly we shouldn't have thrown it away, or why we wouldn't have thrown it away. Okay, so before we get to that, let's ask, what if the particle is moving now? So what if our phenomena is moving? Okay, so what I mean mathematically by that is that what if the free momentum is non-zero? Is the plane wave solution still valid if I set um, my momentum to some definite value, so some non-zero value? And the short answer to that is yes. Okay. I'm not gonna go into the full computation on why that's true, um, but you guys would find out that indeed it checks out. Okay, and if I do plug in and do the math that I did a while ago up above here to find the U's or my energies, so if I find my energies, so if I try to find the energies with P not being equal to 0, we get the non-rest frame energy equivalence relation. So um, if so uh, if my 3 momentum is non-zero, then my so I would get E squared is equal to M squared C to the fourth plus P squared C squared. And you guys can check that out for yourself. And that tells us that, of course, it tells us that the plane wave solution is valid as long as my momentum and my energy satisfies the laws of special relativity. Okay, so what now? We have proved that we cannot just throw away these things, and we've seen what exactly a Dirac spinor is in the context of our study. But now, what does it imply? What's the physics? So what's the physical interpretation of things? So I'll probably make a timestamp. This is probably where you want to jump to the interesting part, the actual interesting part of the video, because I'm not really gonna talk about much math right now. So, right, we have negative states. We have negative energy states and positive energy states. So, if I plug in my usual stuff and then do some algebra, my plane wave solution, I get that my psi is equal to some normalization constant times times potential energy U. So U spinner. This is my spinner, right? So U times. It's a bit hard to write here. I'll try my best to write it down for you guys. So C times the Pauli spin matrices times my 3 momentum, contract my 3 momentum over MC squared plus lambda. Wait, no, you guys can confuse that over there. MC squared plus lambda E, and then this is times U. Okay, wait, I'm gonna write that in my square bracket notation. Okay, and then this is multiplied to an additional factor of, so x of I times 3 momentum times my x minus an epsilon t over h bar, and that's all over the square root of 2 pi h bar raised to 3. We're in my epsilon now. So my epsilon is equal to plus minus E. So that's to take into account the positive and negative branches of our solution. And of course my E is, it's the same thing. It's my energy. So square root of C squared P squared plus M squared C to the fourth. And then my lambda is essentially the sine function of my epsilon. So if my epsilon takes on, so my epsilon is essentially my E, right? So if my E is positive, then this over here is a positive term. And if my E is negative, this is negative as well, okay? That's what my SJ means. So, of course, this implies that we have two types of quantum object, right? Or rather, we have two energy states for two different kinds, or two fundamentally different kinds of energy states for our object with wave function phi. So, how Dirac thought about it is that, okay, instead of considering it to permeate um, space alongside its negative energy counterpart, let's consider a sort of sea or a sort of plane wherein each each of these positions over here is an energy state of, say, an electron, or say in our context a femboy, right? So this is my energy, this is the positive part, this is the negative part. And let's say that, and actually Paul Dirac used the Pauli exclusion principle as a justification to say that, okay, let's say that the particle occupies all of space. So every single one of these points are occupied by a special electron. So a unique electron with certain energy, you know, E. And of course, each of these electrons can move down one step in their energy. But of course, there's gonna be the threshold. Let's see, this one over here, wherein each of these guys are gonna jump to a negative energy. Okay. There. Of course, there's gonna be a chance that one of these is gonna jump to the negative part of the sort of the plane. Of course, this is called the Dirac Sea nowadays. And excuse me. Yeah. So right. Okay. So I'm just trying to recall my surface because I'm doing this late at night and my brain is practically mush. Okay. So um, there's gonna be a chance. So there's another chance that each of these guys would have an empty spot. So there's gonna be an empty spot. There's a chance that each of these guys. So when I move an electron down, so there's a chance that the electron would simply just go out of the well, or it's gonna move down into a spot. So this planes extends to infinity. So let's say that this one of the electron over here moved. Oops, the electron here moved down. Okay, and we have a we have an empty spot essentially. As we have an empty spot essentially. So what are we to do with that empty spot over here? So okay, instead of thinking it as a lack of a particle, let's say that it is an like evidence of a particle. Okay. So what Dirac was essentially telling people back then was that, okay, all of these filled spots are the electrons themselves. But an empty spot over here, so I'm gonna call it a blue. So blue. So this encircled spot over here, this empty spot, is another kind of particle, a so-called antiparticle, wherein although it has the same energy as it would the previous electron that was in its spot, it has a negative um, value for it. Okay, so especially one's over here. So if this one moves, so if this electron moves down, if this one moves down, there is an empty spot in it. So it would be the sort of counterpart to it, the negative energy counterpart to this electron over here. Okay, so what they said, so it is said that what Paul Dirac um, proposed, of course, essentially, is that these empty spots are the counterparts to each. So if a femboy permeated every bit of space due to the Pauli exclusion principle, the lack of a femboy is essentially what we call a tomboy in this context. Okay? So that lack of a particle, which is claimed to be an actual particle, is then called a positron. So if this is an electron, this lack of an electron is called a positron. And really, it's amazing that they were able to think about this back then, because um, as far as we knew back then, stuff had to be definite. This sort of concept of a whole being characterized as a new type of particle, it's totally alien. This is new. This is something that people hadn't thought of before. I mean, perhaps maybe by some people who were pipe smoking, but it wasn't seriously considered until Dirac proposed it. Okay, so now if we want to apply this to our theories, of course, I have the same Dirac Sea, but instead, the sea is permeated with a bunch of quantum femboys or quantum phenomena. Okay, so it can be time, it can be space, whatever. It doesn't matter. The point is, all of space is permeated by a bunch of quantum femboys. Okay, so each with their own respective energy levels. Okay, if a femboy leaves or moves down a rung in the energy ladder, of course, there's going to be a lack of a femboy. So there's a lack of a femboy. So let's say each of these is a quantum femboy. So the lack of a quantum femboy is now what we posit. So following the analogy or following the physics, it's a quantum tomboy. Because these are polar opposites of each other. So it would make sense that, of course, just like how the positron is the polar opposite of an electron, albeit they have the same energies, so to speak. They have the same vibe. I wouldn't like to associate energies with vibes, like the hippie stuff, but what we mean is how we characterize them are essentially the same, but polar opposites of each other. The same thing with how electrons and positrons have the same type of charge, but the sign is reversed. Now, I'm not associating, actual femboys um, with electrons and tomboys with positrons, but the upshot is that we can express these guys as systems that act in a similar manner. So, yeah, there's that. So it's the Dirac Sea. And that's essentially what I was leading up to in the last lecture. Okay? So in the Dirac Sea, there's a quantum femboy. If the femboy leaves or shifts in energy and leaves an empty spot, that empty spot simultaneously becomes a quantum tomboy. And the rules could be reversed essentially. So if a tomboy is occupied, that occupation is essentially by what? A quantum femboy, essentially. So, again, I can switch the roles and say that the quantum tomboy is that particle over there, and the lack of a quantum tomboy can be a quantum femboy. It's reversible, just like in the Dirac Sea with electrons and positrons. If there's a lack of an electron, and then if there's a lack of an electron, ergo a positron, and I put an electron in it, there's an electron there, essentially. So, there's that. So, I mean, if I say the positron is the existence, so the one that exists, right? And then I characterize the electron as a lack of a positron, and it works the same way. The physics is still there, and nothing breaks down. Okay, so, and because of the fundamental nature of the wave function, we're still able to find probabilities. We're still able to do the physics that we used to do back in Schrodinger, back in the days of non-relativistic Schrodinger equation and wave functions. And that's what's neat about what Dirac did, and that's why I really I want to reach to you guys how ingenious Paul Dirac really was. Now, the thing is, some people find this inelegant, really. And you can find it in Wikipedia. So, I mean, I'll just read from it. Despite its success, the idea of the Dirac Sea tends to not strike people as very elegant. So, um, what this essentially saying is that the negative the negative part of the plane stretches out to infinity, just like the positive one. But the fact that it stretches off to infinity doesn't really strike people as nice, um, because we don't know what the absolute energy density is. So we don't know at the scale of the cosmos what exactly is our negative and positive energy states, right? So people don't find it particularly elegant because of that. But with the development of quantum field theory, we essentially reformulated stuff, in our Dirac equation. So the Dirac equation still stays the same, and the wave function is still a wave function, but instead of it simply being some sort of wave or whatever, it's a probability density. We now think of it as a quantum field. So I discussed in the last lecture that you guys should think of the wave function as a field, right? It's a function of space and time, right? But um, it's much more in depth than that, essentially. Okay, so with quantum field theory, we can say, um, we can now talk about, we could talk about, so during the time of Paul Dirac, he didn't directly say that the lack of a particle is a particle itself, right? He simply said or labeled that lack of a particle as a positron. That's what he said. But with quantum field theory, we were essentially able to say that this lack of a space, or so this lack of a quantum femboy, is an actual entity called a quantum tomboy. So the lack of an electron is something that's actually called, it's an actual particle called a positron. So when the electron left, a positron occupied the space. Instead of there being no particle at all, there is a particle over there that came as soon as the electron left, right? Okay, so um, this is so what I'm gonna say now is gonna practically wrap up our sort of dive into some field theory. Okay, and in the next lecture, we're probably gonna be going back to actual string theory, and maybe we'll discuss about the standard internet model for phenomena, or the SIMP. Okay. So the thing is, okay, we have fields, right? And we know today that in space, of course, we have particles and antiparticles coming into fruition and then essentially coming together and annihilating, right? So, in order to characterize that mathematically, what we essentially need are creation and annihilation operators, right? So, in the modern interpretation, our Dirac Sea can be reinterpreted as a very simple type of something called the Bogoliubov transformation. Bogoliubov. That's a mouthful, but that's what it is. So, what is a Bogoliubov transformation? It's an identification between the creation and annihilation operators of two different free field theories. So, um, while in our original theory with Paul Dirac, we were talking about individual particles or wave functions of individual particles. We're now talking about different field theories. So to each field, so from particle we turn to field, right? So from each field, there's an associated field theory. Okay, so with the field theory, there's supposed to be its own action, etc., etc. So Lagrangian action, etc., etc., and maybe even the gauge theories of that field theory. But what's important is that there's an individual sort of physics surrounding each of these fields, okay, compared to the physics that we have for individual particles. So it's more general, but here with quantum field theory, it's more specific and localized. Okay. So yeah, we're essentially summing now over two operators of two different field theories. So our interpretation for the Dirac spinor is still a sum, albeit we're not talking about A. So A is still Dirac spinor, but we're not talking about we're not talking about E as an annihilation operator or a creation operator acting on the Dirac spinors. So that's not alpha, but rather A. So conjugate, so of K. So K is essentially like the function of E and P, right? And this is my E I to the K X, and then plus A, so regular. Okay, so E to the minus IKX. So this is my creation operator, and this is my annihilation operator. Acting on my Dirac spinor or my field theory. So field theory 1 and then field theory 2. Not 2, not 1. So the operator with a negative frequency lowers the energy of any state by an amount proportional to the frequency, while the operators will with positive frequency raise the energy of state. That makes sense because we have annihilation and then creation operators. Okay. So now there are different types of fields. Of course, there are fermionic fields, there are bosonic fields. Of course, fermionic fields involve quarks, leptons, gluons, etc. And our bosonic fields essentially represent our bosons, Z, plus minus bosons, etc. So of course we're gonna go in depth with that when I discuss the standard internet model for phenomena. So essentially that's it. So yeah, there's that. So that's really it. Okay, so I know it's a bit slow because my brain's a bit slow right now. Okay, I'm practically not thinking right now. So I could be saying some stuff wrong, but essentially what I want to reach out to you guys is that this concept of the Dirac Sea and our polar opposite internet phenomena. And by internet phenomena, of course, I mean femboys, MILFs, or what have you on the internet, cat boys, cat girls, whatever. Each of these guys are related to each other using the Dirac Sea, and the fact that they are manifestations of the mathematics behind our application of the Dirac equation. Okay, so yeah, that's really it for this lecture, and I'll see you guys in the next one.